Here are some examples that we would like to use limits to find their bounds. So let's solve the first question. In this example, you are given two functions, n plus 1 and n squared. If we want to use basic definition to prove that f of n belongs to big O of g of n and g of n does not belong to big O of f of n, then we need two steps. One, we use basic definition to prove this part, and we prove by contradiction to prove this part. But now if we want to use limits, then we can do it in one step, because limits can tells us that if f of n belongs to big O of g of n, then g of n is never big O of f of n. So let us find the limit. Now here we need to find limit when n goes to infinity for n plus 1 over n squared. This is equal to limit of n goes to infinity, and we divide n over n squared plus 1 over n squared. This also is equal to limit as n goes to infinity of 1 over n plus 1 over n squared. Now distribute limit over these two terms, and we will get 0 plus 0 is equal to 0. Now since the answer is 0, remember we say that n squared grows faster than n plus 1. So we say that n plus 1 belongs to big O of n squared. And also the reverse is not true, because as we mentioned that if you use limit, then if one function is big O of the other function, then the other function is impossible to be big O of the first function. And n squared is not equal to big O of n plus 1. In the next example, we have a polynomial of degree 8, and we would like to show you using limits that this polynomial belongs to big theta of the dominant term, which is x raised to power 8. Use this example as a guide to prove the polynomial theorem, which states that every polynomial belongs to big theta of its dominant term. To prove that this polynomial belongs to big theta of x raised to power 8, we take limit as x goes to infinity, x raised to power 8 plus 7x raised to power 7 minus 10x raised to power 5 minus 2x4 plus 3x square minus 17. We divide the polynomial by x raised to power 8. Now divide every term of the polynomial by x raised to power 8. That means we can divide each of these over x raised to power 8. So the answer will be equal to limit as x goes to infinity. We will have x8 over x8 plus 7x7 over x8 minus 10x5 over x8 minus 2x4 over x8 plus 3x square over x8, finally minus 17 over x8. Now simplify each term. So x8 over x8 will be 1 plus 7x raised to power 7 over x raised to power 8 will be 7 over x minus, usually we take the difference of the powers. So here we have 8 minus 7, so x raised to power 1. 8 minus 5 is supposed to be x raised to power 3. So it's going to be 10 over x raised to power 3 minus 2 over x raised to power 4 plus 3 over x raised to power 6 and minus 17 over x raised to power 8. You have learned in calculus that limit as x goes to infinity for 1 over x raised to power n is equal to 0 for all n positive, and as a result the limit when s goes to infinity for all of these terms is equal to 0. So we write here that the answer is equal to 1 plus 0 minus 0 minus 0 plus 0 and minus 17, which is equal to 1. Now since 1 is finite, not equal to 0, so we say that f of x belongs to big theta of x raised to power 8. In example number 3, we have a function that involves log. And here we have log of n that is raised to power k, and k is a natural number. We need to prove that such function is always belongs to big O of n. This function lg raised to power k n is in fact log 2 of n altogether raised to power k. So lg raised to power k of n is in fact log of base 2 of n raised to power k. So it's a power function of log. In this example, we are going to apply L'Hopital's rule. Therefore, it is required that we take derivative of log 2 of n. Finding the derivative of log 2 is the same as finding the derivative of len, except that we divide the answer by a constant, which is len 2. Therefore, it is better that we convert log 2 into len and work on the derivative of len instead of the derivative of log of 2. So how to convert log 2 of n into len? You write log 2 of n, it's equal to, now you want to convert it into len of n. You know that len has the base e. So therefore, you have to multiply len of n by a constant, which is log 2 of e, which is the base of len. Now suppose, for your information, you want to convert log 2 into log 10 as an example. So log 10 has a base 10, so you need to multiply the answer by a constant, which is log 2 of 10. So to convert log 2 into len, we will use this expression. So our target equation, which is log, so our equation log 2 of n raised to power k, when we substitute it by log of 2 of e multiplied by len of n raised to power k, it is going to be equal to log of 2 of e raised to power k multiplied by len of n raised to power k. Now this is constant, so therefore we will say that this is equal to a constant multiplied by len raised to power k of n. So let us start the proof. So we need to find the limit. We have a constant multiplied by limit as n goes to infinity, and we write len of n raised to power k divided by n. Now you know that when n goes to infinity, this is equal to infinity, this function is equal to infinity, and when n goes to infinity, also n goes to infinity. So we will apply L'Hopital's rule. Here I will say apply L'Hopital's rule. So what is the answer we will get? We will get a constant limit of n goes to infinity, and the derivative for this len, first we multiply k by len of n raised to power k minus 1. So we have len of n raised to power k minus 1 multiplied by the derivative of len, which is 1 over n, divided by the derivative of n is equal to 1. Let us rearrange the equation. So this is equal to c. Now this is a constant. You can take it outside. and we have limit as n goes to infinity, and we will have len of n raised to power k minus 1, and now this is 1 over n will go down, so we will divide this equation by n. Again, we apply L'Hopital's rule, so apply L'Hopital's rule. After you apply the L'Hopital's rule, what you will get c multiplied by k limit as n goes to infinity, and the derivative for this function will be k minus 1 multiplied by len of n raised to power k minus 2 multiplied by the derivative of len, which is 1 over n, divided by the derivative of n, which is equal to 1. Now, rearranging the equation, this is equal to c. This is a constant, so take it outside. It will be k multiplied by k minus 1 limit as n goes to infinity. Rearrange this equation, the part of this equation. So this is equal to len of n raised to power k minus 2 divided by n. Again, apply L'Hopital's rule, and we will have the following: c multiplied by k minus 1 limit as n goes to infinity, and the derivative for this function will be equal to k minus 2 multiplied by len of n raised to power k minus 3 multiplied by the derivative of len, which is 1 over n, divided by the derivative of n, which is equal to 1. Rearrange this equation. This is a constant, you can take it outside. So this is equal to c multiplied by k minus 1, k minus 2, limit n goes to infinity. We will have len of n raised to power k minus 3, and for this part n will go down, so we will divide this equation by n. You keep applying L'Hopital's rule repeatedly. So here again, apply L'Hopital rules, and when you apply this L'Hopital's rule repeatedly, then this power will keep decreasing. It will keep decreasing. So if it is, for example, 5, then it will be 4, it will be 3, it will be 2, then it will be 1. So after you apply L'Hopital's rule repeatedly, eventually at the end you will reach the following equation: a constant multiplied by k minus 1 by k minus 2 multiplied by 3 multiplied by 2, and then we will have multiplied by limit as n goes to infinity for len of n over n. To understand on how did we get these multiplications, imagine you have the following equation or function: x raised to power 4. Now if you take derivative, then it will be 4x raised to power 3. Now if you take derivative again, then it will be 4 multiplied by 3 by x raised to power 2. Take derivative again, it will be 4 multiplied by 3 by 2 by x raised to power 1. So this is the value for the first power, and it keeps decreasing. And this is what's happening here. This was the first power, and the power was decreasing, and every time we take derivative, we multiply the power with the previous power until the one that is before the last derivative, which is equal to 2. So this is why here we have 2. Now if you continue, take derivative of this equation, len of n over n, and the equation will be equal to, again, c multiplied by k minus 1 multiplied by 3 by 2. And after applying L'Hopital's rule, then it will be 1 over n over 1, which is equal to c multiplied by k minus 1 by 3 by 2 limit of 1 over n. And you know that limit when n goes to infinity for 1 over n, which is this one, it is equal to 0. So I will just cloud it. Now since this one is equal to 0, so therefore the answer of this limit is equal to 0. Since we have a limit is equal to 0, then we can conclude that this function in here, that this function is big O of n. And here we can write it as a conclusion that log of k base 2 of n belongs to big O of n. So as a result, if we have a log of n for any power, then it is always part of big O of n. In the last example, we are given two functions, f of n and g of n, and the question is required to show which of these functions grows faster. To get to the answer, we are going to use limits. To find which function grows faster than the other one, we need to take limit as n goes to infinity for f of n over g of n. And this is equal to limit as n goes to infinity. So we will have n squared over 2 raised to power n. Since the limit for n squared when n goes to infinity is infinity, and limit for 2 to the power n of n goes to infinity is infinity, so we have infinity over infinity, so we can apply the L'Hopital's rule. So here we say apply L'Hopital rule. And when you apply the L'Hopital's rule, we will have limit as n goes to infinity. First, we need to find the derivative for n squared, and it is equal to n divided by the derivative of 2 to the power n, which is equal to ln 2 multiplied by 2 to the power of n. Again, we are going to have infinity over infinity, so we will apply L'Hopital's rule one more time. Apply L'Hopital rule. And when you apply L'Hopital rule again, you will have limit as n goes to infinity. Now the derivative for 2 multiplied by n is 2, and we have a constant 2 multiplied by the derivative of 2 to the power n, which is equal to ln 2 multiplied by 2 raised to power n. Now rearranging this equation, take the constants outside. So this is a constant. Take those constants outside. We will have 2 divided by ln of 2 raised to power 2 multiplied by limit when n goes to infinity 1 over 2 to the power of n, and this is equal to 0. Why it's equal to 0? Because this part, the limit, is equal to 0. How? Because 1 over infinity, when n goes to infinity, so 2 to the power n is infinity, so we have 1 over infinity is equal to 0. So now the answer is 0. So what does this tell us? It tells us that g of n is larger than f of n. This is why we are obtaining 0. So since g of n is larger than f of n, then g of n grows faster than f of n. So here we say that g of n, which is equal to the power n, grows faster than f of n, which is equal to n squared. However, of these functions are the running time of two algorithms. Then which one is faster? Now, since this function grows faster, then the running time of this algorithm is larger than the running time of this algorithm. So the running time for f of n is smaller. So we say that f of n is faster than g of n. So don't get confused by using the word faster here. So when we talk about the growth of functions, then this function grows faster. And when we talk about a running time of an algorithm, then we say this algorithm is faster. To get a practice on using limits to find bounds between two functions, here I have provided some exercises, two exercises. In each case, indicate whether f belongs to big O of g, f belongs to omega of g, and if this is both correct, then f belongs to big theta of g. Again, use limit. So take limit when n goes to infinity by dividing f of n over g of n and see the result. If it is 0, then f of n belongs to big O of g of n. If it is infinity, then f of n belongs to big omega of g of n. And if it is finite other than 0, then f of n belongs to big theta of g of n.